Hello, everybody. Welcome back for this other lecture that continues a topic that we started discussing last time, which is the inverse of functions. So we saw functions are such an important concept and we can deal with them very rigorously and even a little bit beautifully within the confines of set theory. So we're just going to build on what we were doing. The topic we were discussing towards the end of last lecture was inverses of functions, right? So what's an inverse function? As you'll remember, it's a function that undoes what a given function does, in which case the second function, the one that undoes things, is the inverse of the one that is given to begin with. Now, as we discussed, some functions have an inverse, and if they do have an inverse, then it's unique, but some functions don't have an inverse. And I talked a little bit about the fact that I don't like the way people usually talk about it in terms of whether the inverse exists. I mentioned that all functions have an inverse relation, and that's really when we're asking if an inverse exists, we're asking whether the inverse relation is indeed a function. All right. So we've introduced a definition. We looked at some of the logical consequences of those definitions, but then that leaves us with an important problem, which is how can we tell whether a function has an inverse or not? Now, in simple cases, we can just apply the definition of an inverse and just look at all the pairs in the function, construct the inverse relation really, and check that in fact it is a function. So it satisfies totality and uniqueness, which are those two properties that make functions such a special kind of relation. But sometimes functions will be more complicated, and it's going to be a little bit more difficult to proceed in this way. So what we would like is to have a more manageable criterion to determine whether a function has an inverse or not. So what we're going to do in this lecture is introduce a couple of definitions that are going to allow us to decompose the problem of figuring out whether a function has an inverse into two simpler problems. And then for each of those problems, we're going to introduce a concept that gives us a fairly straightforward criterion to determine if a function has an inverse or not. Okay, so those definitions that we're going to start from are the following, namely a left and a right inverse. So the idea is that we're going to start with a function from A to B and a function from B to A. So as we see, since the function G has the domain and the codomain of F swapped, that means that G is a candidate for being an inverse function. And we're going to say G is a left inverse if and only if the composite G after F equals the identity function of A. Remember, the identity function of A is the function that takes an object X in the set A and returns that object X. So it does nothing. That's the do nothing function. And then we looked at how to think about composite functions. And what we have is that if we take an element of the object of the domain of F, X, which is in A, we apply F to it, and then afterwards we apply G, then it returns that object X. So that applying G after we apply F is the same as applying the identity function of A. So that's the precise sense in which G undoes what F does. It undoes it in the particular sense that G applied to the left of F, right, results in the identity function. So that's why it's called the left inverse. And then a right inverse, guess what it's going to be? It's going to be applying G to the right of F instead. So G is a right inverse of F if and only if applying F after G is the same as applying the identity function on B. So in that particular sense, G is a right inverse of F if F undoes what G does. Okay, so now we have the left and the right inverse. And eventually we're going to figure out the relationship between the inverse full stop without qualifiers and those things that I've just defined, namely the left and the right inverse. Now, I want to emphasize that when we were talking about the inverse of f, we saw that it's unique, so we can really say the inverse of f. But a function may have many different left and right inverses. So let's look at an example of how that would work. So here at the top of the slide, I have depicted a particular function from set A to set B. Notice there are more elements in the set B than there are in the set A in this example. And now I'm going to present to you two functions from B to A, G and G prime. And they are going to satisfy this idea of being a left inverse, right? The first function, G, sends both B1 and B2 to A1 and B3 to A2. The second function, G prime, also sends B2 to A1 like the first one and B3 to A2 like the first one, but now it takes B1 and sends it to A2. So now we have two possibilities because there are more elements in the codomain than there are in the domain. So there's this one thing that we have a little bit of freedom to deal with. So imagine we take element A1 and we first apply F to it. That gives us B2. And then we apply G to B2. That is going to send us back to A1. Aha, that's the identity on A. If we apply G prime, again, we're going to take B2 and send it back to A1. Aha, that's the identity on A, it seems. Same thing is going to happen if we start from A2, go to B3. It's going to send it back to A2. But now G and G prime are not the same functions because they are not the same sets of ordered pair. Right? G contains the ordered pair B1, A1, whereas G prime contains the ordered pair B1, A2. So we have two different functions that happen to be left inverses of F here. I hope that makes sense. So based on those two very basic definitions of left and right inverses, we can start building our criterion to determine when a function has an inverse, full stop, an inverse simpliciter, as we defined in the last lecture. Okay, so the first theorem that we get, and again, it's very simple, is to say, suppose you're given a function from A to B, and suppose that this function has a left inverse G from B to A, and also a right inverse H from B to A, then it will follow that the left and the right inverses are in fact the right function, the same function. So if F has both a left and a right inverse, then they have to be the same function. Now, how do you prove that? Well, you're trying to show that G equals H, right? So since G is a function from B to A, we can form the composite G after the identity. And since the identity is the do-nothing function, G will equal the composite G after IB. Now, IB, since H is a right inverse of F, F after H is going to be the same as IB, right? So G composite IB is the same, identical to G after F after H. But then we also saw that the composition of function is associative, so we can just move the parentheses. Now, G after F is equal to IA, since G is a left inverse of F by assumption. And so we'll have G of F, G after F after H. Now, this is the identity on A, so we have the composition of IA after H. But since the identity is the do-nothing function, it follows that this is equal to H, so we have G equals to H as a result. We have a second theorem that says F has an inverse if and only if it has both a left and a right inverse. Okay, so where does that leave us? Well, so I told you at the beginning, we're trying to find a criterion to determine when a function has an inverse. And I said we're going to introduce two concepts. Those two concepts were the concept of left inverse and the concept of right inverse. And now this last theorem tells us part of the answer. F has an inverse if and only if it has both a left and a right inverse. Okay, so if it has both a left and a right inverse, they're identical, as we just saw, right? So both the left and the right inverse will happen to be equal to F superscript minus 1, the inverse of F. And that works in both directions. If F has an inverse, then the left and the right inverse will have to be identical with that one. So that's a fairly easy theorem as well. I believe it's proved in the note, but I decided not to include it on the slides. So now we have sort of broken down the problem of figuring out if F has an inverse into two problems. The first, does it have a left inverse? And the second, does it have a right inverse? And if it does have both, then we know it has an inverse, and the inverse is exactly equal to the left and the right inverse. So now we have transformed our problem into two subproblems. What we're going to do next is, well, find alternative forms of those two subproblems that are a little bit easier to deal with. So when do functions have a left and a right inverse? Well, let's turn to that particular question. So some functions have a special property. That property is that they are not many to one. That is to say, it never happens that two different elements of the domain are mapped onto the same element of the codomain. Okay? Another way of saying it is that if f of x equals f of y, right? So I take an element of the codomain, call it b, and b happens to be equal to f of x and f of y. Well, that must mean that x and y are the same. If x and y were not the same, that would mean there would be two different objects that would be mapped on that object B, right? So to say that a relation is not many one is to say that if f of x equals f of y, that means x equals y. This is such an important property for functions that we're going to give functions with that kind of name. We're going to call them injective function. Okay, so we're going to say, suppose f is a function from a to b. Now take any two elements of the domain. If it's the case that fx equals fy implies x equals y, that means f is not a many one function. And that means it's an injective function. There are other terms that are often used in mathematics to describe injective function. One name is that it's a one-one function, and another name is that it's a function that is into. I myself really don't like those two terms, so this is why I really encourage you to use the terminology injective. We're going to see later on that there's a slight variation on the phrase one-one function and that refers to something else. So really, if you use the term injective function, you're going to avoid tons of confusion in the long run. So now we have a definition of what's an injective function. Now, the reason I've introduced that concept here is to connect with what I said we were going to do before. We're going to try to reduce the problem of figuring out if a function has a left inverse or if it has a right inverse to something else. And that's what we turn to now. So here's the theorem about the first theorem that we have about injective functions. So the first is just a preamble to the important theorem. It says, suppose f is a function from a to b and g is a function from b to c. So then that means we can form the composite function applying g after applying f. So g circle f. And that says that f and g are injective if and only if the composite is. All right, so typically you're going to know f is injective, g is injective, and then you can just infer from that, thanks to that theorem, that g of f is injective as well. Okay, so proof is extremely simple, so I'm not going to take time to go over that here. I again invite you to play a little bit with your definition and be able to prove that theorem, but it's very simple. Now we get to the more beefy result, which is to say it helps us to answer the question, when do functions have a left inverse? And now we're going to assume that we have a function from a to b, but moreover that the domain is not empty. Okay, so there's one exception if the domain is empty. But if the domain is not empty and we have a function from a to b, then we can say that f is injective if and only if it has a left inverse. Okay, so since that one is important, let's take a few moments and examine how we would go about proving that. And again, I will do that with a Fitch diagram. The proof in prose is in the notes. Oh no, it is the proof in prose. All right, sorry. So what we're going to want to do again, we have an if and only if. So we're going to say if f is injective, then it has a left inverse. And the second part, if it has a left inverse, then f is injective. So we're going to start with f is injective. And this is why I didn't do it as a Fitch diagram, because that one is we're actually going to construct the left inverse from our assumption. Okay, so the first thing we're going to do is we're going to think of a function from b to a, and we're first going to start with the restriction of the function g to the range of f. And we're going to make sure that at least for the restriction of g that applies to the values of the function f, if we just switch the order of the elements in the ordered pair, that it gives us what we want to do, namely that g undoes f for all those elements that f gives us when we apply it to an element of its domain. Okay, so g is g restricted to the range of f is thus just going to be the inverse relation of f. Okay, so y x in the Cartesian product such that y equals f of x. Okay, now as we saw when we talked about the restriction of a function, we said, all right, we start with a function restricted to a subset, and we might want now to extend it by adding a bunch of ordered pairs so that it's defined over a larger domain. So that's exactly what we're going to do. We're going to start with g restricted to range f, and we're going to extend it to a broader domain. Now, as we saw, there are many different ways of extending a function on a broader domain, okay? So now we're just going to take G to be any of them. Just pick one, all right? And what we're going to do is take that function G and make sure that it has the right property. Now, since G is an extension of G restricted to range F for the entire set B, now we know that G is defined for every element of B, right? So that means that that set of ordered pairs satisfies totality. And moreover, G of y equals x if and only f, f of x equals y by construction in the way that we have defined it here, okay? So now we're going to take just any object in the domain of the function f, and we're going to apply the composite G of f, right? So because we're building G to be a left inverse, right? So we see that G of f first is, by the definition of composition, is G of f of x. Now f of x equals y, so G of y, which is just x. So that means that G of f, G after f, is the same as the identity function on A, and that's what it means for G to be a left inverse of f. So f does have a left inverse, namely G. Now, if you just give me a second, I'll come back a little bit earlier to my first example that we had here, right? So here I have a function from A to B, right? It contains the pair A1, B2 and the pair A2, B3. So when I construct a left inverse, I want to make sure that now the pair B2A1 and the pair B3A2 is in my left inverse. This is why here B2 maps to A1, same for the other one, B2 maps to A1. Similarly, B3 maps to A2, B3 maps to A2. So we just take the arrows that we have for F and we reverse it, right? But now if we just have those pairs, that's not enough to have a function because that wouldn't be defined for object B1, right? So I'm going to start from those two pairs and I'm going to extend my set by adding an ordered pair whose first member is B1 and second member is one of the objects in A. So G takes the first option where B1 is associated with A1, and G prime takes the second option where B1 is associated with A2. So you see, G and G prime are two different ways of extending the inverse relation of f into a function. And that function is going to work as a left inverse, as you can see right here. You start from A, you go to B, and then you take one of the left inverses, any of them, and you return to the same element. So that's the same as just applying the do nothing function, the identity function. So this is the idea of that proof that we have here, right? We start from F, which is injective. And then, by the way, I forgot to write here, G satisfies totality, but it also satisfies uniqueness. Because since F is injective, we know that there's not going to be two different pairs with the same element of the codomain that are there. So when we flip the order, we're not going to end up with a pair, say, BA1 and BA2, which would make uniqueness fail. So uniqueness is satisfied precisely because F is injective. Okay? So I should have written that here. I'm sorry I didn't. So now we have the first direction proved. If F is injective, then it has a left inverse. Now let's flip things around. We're going to assume it has a left inverse, and we're going to try to show that F is injective as a result. So suppose F has a left inverse. And suppose that this left inverse is a function G from B to A, okay? Now, since we want to show that F is injective, remember our definition of injective. It says we take any two objects in A, we suppose that Fx equals Fy, and we try to derive the fact that x equals y as a result. So that's what we're doing here. Take two arbitrary elements, x and y, of the domain of F. suppose that fx equals fy. Now, fx equals fy, we're going to apply the left inverse to both sides of the equation, right? So that tells us that g of f of x equals g of f of y. Because we have one object, g is a function, so it has to send it to one particular object. It cannot be two different objects. Since g is a function, it must satisfy uniqueness. Now, applying the definition of composition of functions, that tells us g after f applied to x equals g after f applied to y. Now, since g is a left inverse of f, that means that that composite here is just the identity on A for both. So IA of x equals IA of y, which just means that x equals y, because this part here equals x, this part here equals y, so x equals y. And since f of x equals f of y now is seen to imply x equals y by the transitivity of implication, it follows that f is injective. So this is how that theorem is working here. Okay, so now we know that a function has a left inverse if and only if it is injective. Beautiful. Now, here's a second crucial property of functions. So we had two problems, left inverse, right inverse. We found a property, being injective, that perfectly matches having a left inverse. And now we're going to look for a second crucial property that we hope is going to match right inverse. And then we're going to say the following. So for some functions, every element of the codomain is mapped onto by some element of the domain, right? So again, I'm going to come back a little bit to that image that we had at the very beginning. Here for f, we have an element of the codomain that is not mapped onto by any element of the domain, okay? So that f is not a function that has the property that we're trying to capture here. Really, that property that we're trying to capture is the range is the entire codomain. Every element of the codomain is mapped onto by something. So that's the idea. That's the second crucial property, and that's going to be called being surjective. So a function from A to B is surjective if its range is its codomain. So that is to say, the range, right, the image of A under F equals the codomain. I could have written the range of F equals B. We saw that last time. That's the same thing. Another name for surjective function is a function that is onto. I also don't like that name very much. I much prefer the name surjective. Another way of saying that a function is surjective, which is exactly equivalent to what was said here, is the following. For every element of the codomain, there is an element of the domain such that that first element of the codomain is the value of f for that element of the domain. So y is the value of f at x, and for every element of the domain y, every element of the codomain y, we can say that it is the value of some element of the domain. That's another way of putting it. And then what we're hoping is that being a surjective function is closely associated with a function having a right inverse. So this is what we're going to say right now, right? So the first theorem is just the same as the counterpart of the first theorem we had about injective function, which is that the composite of two functions is surjective if and only if both functions that are composed are themselves surjective. Also very simple. I just encourage you to play a little bit with the definitions to see that this is indeed true. But really the important theorem that we want is the following. Namely, that if a function from A to B has a non-empty codomain, then we can say F is surjective if and only if it has a right inverse. Now, there is a proof sketch in the notes for that. It might be a little bit surprising, but if we take all the definitions and all the axioms that we have introduced so far in set theory, we still would not be able to prove that theorem. That's a bit shocking, right? Uh, the idea is that in order to prove that theorem, we need another axiom that I sadly don't think we will have time to cover this semester. That would be very fun. It's a very important axiom, and it's the subject of a lot of philosophical fights about the foundations of mathematics. Uh, some people think it's obviously true, some people think it's obviously false. But in any case, it's part of standard Zermelo-Fraenkel set theory, namely ZFC means Zermelo-Fraenkel plus the axiom of choice. Now, if we do have the axiom of choice, then we can prove that theorem here. For the rest of the discussion, for pedagogical reason, I will assume that we have that as an established fact, though it's not established yet. Okay, but in the notes, I show a little bit how we'd use the axiom of choice in order to produce that inverse function. But let's assume that let's not worry too much about where the proof is coming from for now. Now, I just want to introduce a third property of functions, just so we hit the trifecta. And that's going to be called being a bijective function, or a bijective function is sometimes called a bijection. So a function is a bijection, or is bijective. Oh, I confused my terms here. A function is bijective, or is a bijection, if and only if it is both injective and surjective. Okay? So a bijective function is also called a one-to-one correspondence, not to be confused with a one-one function, which is another term for injective, which is why I encourage you to use injective, surjective, and bijective, because it's much less confusing. All right, so a function is a bijection if it's both injective and surjective. Now, bijective has a little bit of a figurative sense, right? Perhaps a geometrical intuition that we could use. Now, in many areas of mathematics and combinatorics and group theory, or even in probability theory, a bijective function with the same domain and codomain, that's often called a permutation. And we're going to see that it just takes a number of objects and put them in a different order. So that's really what a bijection does. And the theorem that we're going to have, the first one is a composite function is a bijection if both of its parts are bijections. Again, easy to prove. I'm not going to spend time doing that. I encourage you to play a little bit to figure it out on your own. But the big theorem that we want to, as you're going to see, relates bijective functions to functions that have an inverse. So let me just first explain what's the difference between injective, surjective, and bijective by comparing three cases. Let's take the first case, right? So here we have a domain with 4 objects, a codomain with 5 objects, right? So every element of the domain is mapped on something in the codomain. Also, we notice that there isn't a single case where 2 different objects are mapped on one object on the other case, right? Each object of the domain is mapped on a different object of the codomain. That makes it an injective function, okay? On the other hand, it's not surjective because there's one element of the codomain, the third one, which isn't mapped onto by any single element of the domain. Okay, so that function here would be injective but not surjective. Now let's look at the second one. Now here we have more elements of the domain than we have in the codomain. That means that There are two different objects that are mapped onto the very same member of the codomain. So that's a many one function, right? So this is why it fails to be injective. But on the other hand, it's surjective because every element of the codomain is mapped onto by at least one element of the domain. Now, so here we had an injective, not surjective. Here we have a not injective, surjective. What happens when we have both injective and surjective? Well, we have that every element of the domain is mapped onto a different element of the codomain. And also every element of the codomain is mapped onto by at least one element of the domain. Now that means that every element of the domain is associated with exactly one element of the codomain, and vice versa. Every element of the codomain is mapped onto by exactly one element of the domain. So you see, the first is mapped on the third, the second on the fourth, the third on the fifth, the fourth on the first, right? So this is a 1-to-1 correspondence, which is the other term to talk about bijective function. So you see that there's something beautiful about that bijective function. And now let's think again a little bit in terms of inverse relations, right? So here we have a function. Take the inverse relation of that function. That wouldn't be a function because it wouldn't be defined for the third object. We would have to produce an extension of it, right? So we don't get automatically an inverse with, so the inverse relation is automatically an inverse function. Now let's take the second case that we looked at and take the inverse relation where we just change the direction of the arrows. Now that wouldn't be a function because the first object would now go or be mapped on both the fourth and the fifth object, which means that the inverse relation would fail to satisfy the uniqueness condition. So it wouldn't be a function either. Right, so here the inverse relation would fail to be total. Why? Because it's not surjective. Here the inverse relation would fail to satisfy uniqueness. Why? Because it's not injective. But so now in this third case here, we can just change the direction of the arrows, taking the inverse, getting the inverse relation, and poof, bingo, automatically the inverse relation is a function. Okay, so this is why this idea of being a one-to-one correspondence is so tightly connected with the idea of having an inverse. So I hope that visual representation helps you to put together all those ideas that we were talking about. Okay, so if you want to play more with those ideas, you can play a little bit uh, um, um, with a theorem that we have proved before. So we have proved before that if f is a function from a to b, and that this function doesn't need an inverse. I don't know why I wrote that. But S is a subset of the domain, T is a subset of, should be of B, right? Of the codomain. Of course, it should be B, not Y, right? Then we found out that S is a subset of the preimage of the image of S. And furthermore, we saw that the image of the preimage of T is a subset of T. And we said that in general, we don't have an identity. We only have one of the two subset relations. But there is a condition that we can impose on the function f that is going to make those identities. And I will encourage you to think of it in terms of that visual depiction that we just went over. Now, we're going to say that S equals the preimage of the image of S if and only if F is injective. Maybe you don't want to make the full proof, but just play with it with some graphical representation. And furthermore, the image of the preimage of T equals T precisely when f is surjective. Okay, and that again is very closely related to this idea of the inverse relation being automatically a function. Okay, so where does that leave us? Well, that leaves us with a series of facts that we have examined that helps us to figure out when is it the case that a function has an inverse, right? So firstly, a function has a unique, well, so if a function has an inverse, it has a unique inverse, right? Uh, and we saw that a function has a unique inverse if and only if it has both a left inverse and a right inverse, in which case they are identical and they are that unique inverse that we were talking about. So we took our big problem of determining when a function has an inverse and we broke it down into two problems, left inverse, right inverse. And then we saw that a function has a left inverse if it's injective, that is to say, it maps different elements of the domain to different elements of the codomain. And then we also saw that it has a right inverse if and only if it's surjective, which means that every element of the codomain is mapped onto by something. And then that leaves us with that conclusion that a function has an inverse if and only if it's bijective, a one-to-one correspondence, like we saw on the pictures. Now, figuring out that a function is one-to-one is much easier. You can really just look at the function, the way it's defined, and it's going to be quite a bit easier to figure out whether it is one-to-one, a one-to-one correspondence, that is to say a bijection. Now, if you do calculus, you've probably also found ways of figuring out if a function is bijective. You might have seen, oh, a function is monotonically increasing or monotonically decreasing. That means it's a bijection. That means it has an inverse, right? We're not going to get into that today because we don't have yet all the tools that are needed to do calculus. But at the end of the day, figuring out if a function is an inverse reduces to it being a one-to-one correspondence. Okay, so what that tells us is that there is only one type of circumstances, when we can undo what a function f does fully, right? And we can only do so if f is a one-to-one correspondence, a bijection. If f is not a one-to-one correspondence, then we cannot undo what f does with a function. That's an interesting thing. And that has applications everywhere that formal methods are used in order to study things, because studying things is done with functions, and then we want to figure out properties of those functions, and whether that function has an inverse or whether it's a bijection is often an absolute cornerstone of doing that. Okay, so that closes it for our discussion of functions. Next time, we're going to introduce the axiom of infinity that's going to guarantee that there exists a set with infinitely many members. We're going to define natural numbers. We're going to define some operations on natural numbers. We're going to learn about mathematical inductions. We're going to prove that it's a good rule of inference. I'm sure many of you know how to make a proof by induction, if you're in mathematics and computer science in particular. But some of you might not, some of you who know how to make proofs by induction might not quite know why induction is a valid rule to make proofs. So we're going to prove that. And we're going to talk about a few more things like sequences, etc. Okay, so stay safe, stay healthy, and see you next week.